Okay, so we're going to continue with our two examples. These are the characteristics that we deduced in the last part of the last video. Case 1 and 2, I'm going to treat case 1 first. We know the characteristics, equation here. We've rewritten them where we can, right, using our information for rho in the previous video, and we've deduced the solution. Right. What we're going to do now is we're actually going to supplement our initial condition to fill in this missing information. Our problems really arose from our initial condition. Our initial condition in this case looks like this, right? But we don't actually have this information here. We simply have that point and then a jump. We actually need the information along this line, and we have to somehow include it in our problem. So that's what we're going to do. Let's also just redraw our characteristics, but let's just focus on the fan-like characteristics that we've got. Done a bit of a lousy job of drawing that nicely, but anyhow. This is our x naught equals naught, our vertical characteristic, and this is our x equals t sloping characteristic. So I've just taken that one and just drawn that. Inside here, we want to fill in our missing information. We want a smooth transition of gradients, essentially, between these two characteristics. Now, the gradient of our characteristics, it's just our initial density, right? That's our characteristics equation, right? That's our initial density, that's T. So, we have to change our initial density from 0 on this side, 1 on this side. We're going to let rho x naught take on all values between 1 and 0. And I'm just going to specify it like that. Okay. The exactly equals doesn't actually matter too much. What this means is that now inside, this is just inside the fan. This is just to supplement the fan. Inside the fan means this in terms of our overall solution. So, inside the fan, our characteristics are x equals rho x naught t. X naught is 0 on the fan, so we don't need this bit. Right? So all I'm doing is I'm copying down my characteristics equation here. I'm dropping the x naught, and I note that this takes on all values here. All right. we do not abandon the idea that our density is constant along the characteristics. So in the fan, this is true. Our initial density stays the same along the characteristics in the fan. That means we can actually deduce our density from our characteristics. This is the equation we have, and we're now solving for rho. This applies within the fan. We know what the fan region is in terms of x and t because we already deduced that in our previous video. We're now able to fill in this part of our solution. And we're done. That's an expansion wave solution. We can sketch it out for different times. Obviously, rho grows linearly between 0 and 1. And let's just sketch it on this one here. It's kind of convenient. We've got rho 0. That's our initial condition. Now let's do rho at 1, say. So 0 up to x equals 0, doink. It's 1 for x greater than t. So let's say t is 1. So x equals 1, greater than. Oops, I should say t equals 0. Black one's t equals 0. The yellow one is t equals 1. Now between here we have x divided by 1 because t is 1. That's obviously just this straight line like so. We can do another one, t equals 2. This isn't going to change, except now we're going to move on to t equals 2 here. Now obviously we've got x divided by 2. That's going to be a more shallow, like it's going to be slope half. But it's pretty obvious what happens. This dot joins up with this dot. Right. And if we want an even later time, you know, we basically just have to fill in the dots. T equals t star greater than 2. All right, so now let's go over to case 2 and look at that.